So 3.5 is about derivatives as rates of change. So what you have to remember when you're doing a derivative is that since it's related to a slope, um, and think of a slope as a rate of change. A derivative is a rate of change, but it's an instantaneous rate of change. So we're going to talk about what the difference is between an instantaneous rate of change, an average rate of change. We'll talk about some physics applications that displacement, velocity, acceleration. We'll talk about those things. There's some business applications. You can even take a class called business calculus, where they look at how calculus relates to business applications. There's a lot of formulas and things that you wouldn't realize that calculus is used for in business. It's kind of weird how you go from business to physics, but it's a very, very useful tool for all those things. Biology, there's a lot of biological applications as well. There's a formula that can estimate the amount of change that happens at or along an interval from A to A plus H. So you might recall that that formula came up, that A plus H formula was a thing. You might recall that from our difference quotient. So this is a little formula that uses, you'll see the derivative in there. So if we want to find the amount of change on an interval from A to A plus H, so we're talking about how that function has changed. So what we're going to do, the approximate change of the function along that is f of A plus H times the derivative at A. Now that has to be on an interval from A to A plus H. So let's think what's happened here. We have changed from A to A plus H. So we've moved an x value of H from A. Now, why is that important? Well, sometimes our function value might be a little bit hard to find at a certain point. And this allows us to estimate how the function itself is changing. So just make sure to write that formula down, and then we'll talk about it. So we know just two pieces of information about a function, that f of 3 is 2, and that the derivative at 3 is 5. And let's use that to estimate what the function's doing at 3.2. Okay, so how could we estimate a value of a function? So let's think about what we know. So our A value is going to be 3. Our A plus H is going to be 3.2, so that means that our H is 0.2. Okay, and those are the main things for us to think about. So let me write down my formula. F of A plus H is approximately F of A plus H times the derivative at A. Now let's plug in our A's and our H's, and then we'll be good to go. Okay, so let's put all our A's and H's in. A plus H we know is 3.2. A is 3. H is 0.2. A is 3. So I just took out all of the A's and H's and put in their values. Okay. Now we know what f of 3 is. F of 3 there is 2. We know what f prime of 3, or the derivative at 3, is. We know that is 5. So let's put those in now. So f of 3.2 is approximately 2 plus 0.2 times 5. Well, 0.2 times 5 is 1, so that's approximately 2 plus 1, or 3. So that just allows us to guesstimate based on the rate of change at a particular point. We can guesstimate a point that's close to it, what might be happening. So it's just a tool. It's not necessarily more than that. We can't do much more than that. But it allows us to just guesstimate some information. Any questions on that one? Makes sense, kind of, right? Okay. Now let's talk about some physics applications. So remember that the position function we call S of t. The velocity function is just the derivative of the position. The absolute value of the velocity is the speed. Now, the velocity being positive or negative, that can be misleading. So just remember that if we actually want to know our speed, it's the absolute value of that. The positive or negative kind of gives us a directional aspect of things. And then remember, if we take the derivative of the velocity or the second derivative of our position, we get the acceleration. And then we will also talk about like the net displacement, which we have to account for where, how far did I go forward, and then how far did I go backwards. So if we talk about how much we've moved along a certain path, it sometimes is a different thing than our position. Because think about it. Let's say, okay, here's the starting line of a race. I'm not a good racer. But let's say that here's the finish line of the race. Okay. Let's say that I went forward 2, and then backwards 1, and then forward 4, and then backwards 1. And then finally I made it to the finish line. Well, my position is I'm at the finish line. But how much did I actually walk, run, whatever, until then? If each one of those units is a foot, I have gone 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, maybe 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I've gone 11 feet. So it is different if they ask you where's your final position or how much did you move along the way. So we will talk about that when that comes up, okay? But just remember, the main thing to remember is that if I take a derivative of a position, I get velocity. Take a derivative of velocity, I get acceleration. If you know nothing more than those items, that's going to be important, okay? Okay, so we've got this model of a ball that is dropping from a height of 64 feet. And they've given us our position function. Now let's analyze that when you're dealing with feet. The acceleration of gravity is negative 32 feet per second squared. So you will see this half of that. You'll see 16 a lot. And that has to do with rules of derivatives and things like that. So you'll see that number quite a bit when it comes to position functions, dealing with gravity, dealing with feet, okay? So we've got this position function after so many seconds. So the first thing they're asking us is what is the instantaneous velocity of the ball when it hits the ground? Well, the word instantaneous, we need to get into the habit. Instantaneous means a derivative. Instantaneous means derivative. So those words you got to get into your brain. Slope of a tangent, instantaneous rate of change, derivative. Those three things kind of all go together. So when they say what is the instantaneous velocity of the ball when it hits the ground, the first thing we need is the velocity equation, which we know is the derivative of our position function. So let's take this function here and take its derivative. The derivative of that, you know how it works. The 2 drops down in front, multiplies by what's there. Power goes down by 1. The derivative of 64 is 0, so that is just our velocity equation. Now, when it hits the ground, if you look at the picture they have provided, when is the position equal to a height of 0? So we're at a height of 0 at 2 seconds. Now, if you didn't know that, let me show you how you could find it. The position equals 0 if you solve for t at plus or minus the square root of 4, but we don't go backwards in time. And so it's at 2 seconds we hit the ground. We have a height of 0. Our position is a height of 0. So even if we weren't provided this equation in this pretty graph, if you want to know where it hits the ground, you would set the height equation equal to 0 and solve, which I did. And now that we know that, for A, we're just going to stick in the time at which we hit the ground. Now we hit the ground at negative 32 times 2, or negative 64 feet per second. So our position function is feet, our velocity function is feet per second, our acceleration function would be feet per second squared. And I think there's even a next derivative that's called the jerk. I don't know exactly what that means, but anyway, I'm not a physicist. I can help the physicists do their math, but I could not interpret what the heck it means. Okay, let's take a look at part B. What is the average velocity during its fall? Well, if we think of average velocity, that word just tells us a normal, good old slope. We don't have to do a derivative. Average velocity is different. At time 0, my height is 64. At time when I stop, which is 2, my position is 0. So I have 2 points. I started out at a time of 0 and my height was 64, and then at time 2 my height is 0. And I can just use the slope formula to find the average velocity, average position over time, feet per second. So that would be 64 minus 0 over 0 minus 2. And I should have probably turned that, but that's okay. And then we get 64 over negative 2, or negative 32 feet per second. So along the trip, my average velocity is negative 32 feet per second. At the exact instant I hit the ground, my velocity is negative 64 feet per second. That's a big difference. It's very important that you read the question. If it mentions instantaneous, we are talking about a derivative. We are talking about the derivative of the position function. If they use the word average, you were talking about a slope from 2 points. So along the entire fall, start to finish. And so that's different, and you have to make sure that you're answering the question that they have asked. They could ask us the instantaneous velocity at 1 second, the instantaneous velocity at 1.5 seconds. But you'll notice that the average velocity is over a time interval. There's a starting time and a finishing time. Okay, so that's the main thing to look for. Any questions about that example? Okay. Let's take a look at example 335. We've got a particle moving along the position function s of t. They want us to find the velocity at time 1 and the acceleration at time 1. And what does that tell us about the function? So first let's answer those two, and then let's interpret them and let's answer A and B. Okay. So remember, if our position function is t cubed minus 4t plus 2, our velocity function is 3t squared minus 4. Just take that first derivative. And our acceleration function is 6t. Okay. You'll notice every single time our highest power goes down by 1. So that should be something that happens. Okay. Now, what is v of 1? The velocity at 1 is 3 times 1 squared minus 4, or negative 1. Now that is the instantaneous velocity at time 1. The instantaneous velocity at time 1. Okay. Now let's do the acceleration at time 1. Okay. Now, some interesting things. If the velocity and the acceleration are acting in the same direction, your item will be speeding up. If your acceleration and velocity are working against each other, your item will be slowing down. So if it says, is this particle moving from left to right at time 1? Well, okay, so first, what does this mean? This means that it's slowing down because they are opposite signs. Okay, now let's actually go and read our question. Is the particle moving from left to right or from right to left at time 1? Okay, so if the velocity is negative, we are going backwards. So since the velocity was negative at time 1, we are going backwards. What is backwards in this particular event? We want to travel to the right. So instead of going from left to right, we're going from right to left. So we're going backwards. Okay. So that's what the negative part tells us.
If you were to plug 2 in there, you'd be 6 to 4, which should be ordered. So which want to be left to right?
Yeah, at different times. Okay, so what's happening to this particle?
I see what you're talking about.
Yeah, this particle is kind of like that weird example I was telling you. This particle's going, it's going back and forth. You know, it's wiggling. Okay, and then in part B, it says, is the particle speeding up or slowing down? And we kind of answered that ahead of time. I said that if these two are opposing directions, we know that it would be slowing. If they're the same sign, it is speeding up in that direction. So if they're both negative, it's speeding up in the negative direction. It's going faster backwards. If both of them are positive, it's speeding up in the forward direction. So it's going to be slowing down because they're working in opposite directions. So a weird sort of thing. Now, in that same realm, if we looked at how it's traveling, you know, when is it going forward and when is it going backwards and what's its path along a certain way, we may have to draw a picture. We may have to do, remember those plus and minus charts. So the plus and minus chart becomes important again from when we did them last year. You will see those plus and minus charts happen quite a bit throughout this course because we just need to know how things are moving. Okay, so let's look at 336. So we've got this position function. It mentions that time is positive because we're not going to go backwards in time. And it says the first thing says to find the velocity equation. So that's the easy part. Just do the derivative. So we're going to do 3t squared minus 18t plus 24. Okay, so we got the velocity equation. That's not bad. Now this next thing it says, at what time is the particle at rest? So anytime they say that, the first thing I want you to pop into your brain is it is when the velocity equals 0. So the particle is at rest when its velocity is 0. So when will 3t squared minus 18t plus 24 equal 0? Now, you can use whatever method you want in order to solve that. So if you like the quadratic formula, fine. I would say try to factor it. So if you factor out a 3, we're left with t squared minus 6t plus 8. And then it does factor to be t minus 4 and t minus 2. And so we get t equals 4 or t equals 2. So there are 2 times that this particular function stops, where its velocity is 0. Okay, now let's look at part C. On what time intervals is the function moving from left to right? Again, we're going to go left to right is the positive direction. Just think of the number line. And right to left is the negative direction. So here's where the plus or minus chart unfortunately comes into play. So we're going to make a little chart here. And normally I would put on the chart I would put just 2 and 4. But since we do have a starting place of 0, let's put 0 on there. And then we're going to make a little chart. We're going to do our t minus 4. We're going to do our t minus 2. When we plug in 0, we get a positive number. So at 0 right here, it's positive. Let's put a little positive there. Okay, so let's just make up our chart. Okay, so let's plug in 1, 3, and 5. We're just going to plug in some numbers within that region so we can see, well, where's it positive, where's the velocity negative, and so on. If you plug in 1, you get -3 and -1. 2 negatives make a positive, so that's positive. If you plug in a 3, you get a negative and a positive. 1 negative makes a negative. If you plug in 5, you get a positive and a positive, which is a positive. Okay, so it says, where is it going from left to right? Where is it going from right to left? So the positive section, so we're going to go left to right and make ourselves a little note. That's positive. That's going to be from 0 to 2. And then again from 4 to infinity. And then it's going to go backwards from right to left, just from 2 to 4. Now, I don't use brackets, even though those points are acceptable points that work in the function, because those are the switchover points. Those are the zeros, and that's not a point where it's positive or negative. It's just kind of that in-between sort of thing, okay? So that's where we can say it's going from left to right and right to left. So that's what you would do for C, okay? It says, use the information obtained to sketch the path of the particle along a coordinate axis. So this is kind of interesting. Now remember, the path that it moves in is the s of t, okay? So let's we're going to make a very crude, you see how I draw things. We're going to make a very crude picture, okay? So for D, what I want you to do is I want us to look at the switchover points, okay? So at 0, so at the starting position, we are at 4, right? The starting position, we are at 4. So I'm just going to start kind of plotting it out, okay? By position at 2 seconds, so if you plug 2 in, you get 24. So would you agree that from 0 to 2, we have moved forward a position of 20 units? Okay. Now, let's keep going. Now, we're going to go backwards, but how far did we go backwards? Well, if you plug in 20, or if you plug in 4, we get a value of 20. So we went back some, right? Okay. So let's make a little chart. And I'm going to count by 4s. Okay. So it starts at 4, and then it travels to 24, and it's going forward. And then it loops back and it goes to 20. Oh, don't do that. It loops back and goes to 20. And then it will be going forward now for the rest of its existence. So it's just a very crude little picture about what's happening. So at time, and you can even label it. This is at time 0. This is at time 2. This is at time 4. So from 0 to 2, it's going forward until it hits a distance of 24. And then it goes back to 20, and then it keeps going to go forward for the rest of its existence. And given that the original equation is a cubic keeps getting higher and higher and higher eventually. So it's going to just keep going. So that is a kind of just how a position, velocity, how you can interpret its movement. Kind of strange, kind of something interesting to wrap your brain around. Any questions about example 336? So that physics applications, position of things, think about, well, I can't tell you everything yet, but eventually we'll be able to go backwards. So if you know the acceleration of something, Newton was able to work his way backwards and find a position function for it. So that's where it's very powerful. We know the acceleration of gravity, so we know, and then it even goes up to positions of smaller things and how that relates to it, like microscopic sort of things too. Okay, anyway, so there are biological applications to this stuff. If we have a population equation, and if we want to know the population per unit of time over a certain time, that would be an instantaneous rate of change of the population, or the population growth rate. So instantaneous is one thing. And you can use some of that, what's it called? The very first equation I gave you today, that one about the amount of change. We could predict the amount of change over time if we knew certain things. So it can be pretty powerful. But just like our exponential growths and decays are related to biology, population models occur. They try to predict what our population of this is going to be, whether it's a biological material like a virus. We've seen a few of those in our time, or whether it's a people, same thing. They try to predict those things. So let's look at this equation. The population of a city is tripling every 5 years. If its current population is 10,000, what will its approximate population be 2 years from now? Okay. So let's think about what we know. Okay. At time 0, the population was 10,000. Okay, so that's one piece of information they gave us. And if we count it in thousands, we could even do, to make it even mathematically easier, we can say thousands. Okay. What else do we know? Well, we know that the population in 5 years should be tripled to 30,000. So we'll just go 30. So let's approximate what we know the derivative is going to be. Okay, so let's go back to this formula. F of a plus h is approximately f of a plus h times f prime of a. And let's solve it for this. So we would say that f of a plus h minus f of a. This is going to make your brain hurt, and I love it so much, is h times f prime of a. And f prime of a is approximately, oh my gosh, I think we've seen this lovely, disgusting piece of work, that the derivative is approximately, we know that. Okay. So let's think about what we know about, let's see if we can estimate, instead of f's, we'll call them p's, but do we know the derivative at 0? Okay, let's see if we can find that. That's going to help us, okay? So, okay, so so what's h? Let's go from there. Okay, so remember, we don't know much. We know these two pieces of information. Okay, so we know a is going to be 0, a plus h is going to be 5, so h is 5. Okay.
Did you get?
You okay?
Yeah.
Am I okay? Okay. So we know p of a plus h minus p of a over h is p of 5 minus p of 0 over 5. So p of 5, they told us, was 30. P of 0 is 10 over 5. The derivative at 0 is 30 minus 5 is 20. 20 divided by 5 is 4. So if we guesstimate, we could say that the original derivative is 4. Okay, now how can we use that? We're going to use that to our benefit. We're going to use the formula again. But this time we're going to estimate what's happening 2 years from now. Okay, so now how does that change? Okay, so this time, let's go back to the formula. Okay, this time I want my a to be 0 still, because that's where I got the most information. And my h is going to be 2. Now let's plug into the formula again. I took out the f's, I put p's, so we knew what we were looking at. Okay, so this is p of 0, the population of 0 plus 2, which is 2. That's what we're looking for, is the population of 0 plus h, which is 2, times the derivative at 0. Well, we got all those things. So by guesstimating what the derivative of 0 is, we can now predict what the change is going to be at 2. So the population at time 2 is going to be approximately 10 plus 2 times 4, or 10 plus 8, or 18,000 people. People? Did it say what it was? Yeah, people. So it is all a guesstimation here, okay? We're using the information that we know to guesstimate something that we don't necessarily know. So you're going to use this to find our initial change or our initial derivative so that we can apply the formula and then predict what's happening at 2 years. Now, how accurate is that? It's not a great approximation, but it will give us at least an estimate of what might be occurring. Okay. Now, we'll stop. Well, maybe not. Do we just have one example?
Yeah, we just have the business applications.
Yeah, then we'll try it. We'll see what we get. Okay. Now, so we've seen some physics applications. We've seen some population biology type applications. Now let's talk about business applications. If cost of an item is C of X, the marginal cost is the derivative. So marginal cost is the cost per unit of time. Now, why do we need that? Well, because it's going to help us guesstimate the profit over time. And profit is, of course, something that a business is very concerned with. So there's usually you're given you're able to come up with an equation for how much a product costs, how much money we're bringing in. So the profit is just the subtraction of those two. But what a company wants to know, based on the information that we got, what would our profit expected to be over time? So it's just the derivative of those things. So, and they use the word marginal, and that just means over time. So that just means over time. So this is the main thing to know, that the profit is revenue minus cost. So the expected change in profit over time, or the marginal profit, would just be the derivative of that equation. So, think about revenue. How much money am I bringing in? How much did it cost me to make those things? That's my profit. That makes sense, right? So my estimated profit over a unit of time would be the derivative of that. And when we have two equations, we know we can just take the derivative of each individual piece and subtract. So there's lots of words there, but basically if you know what the profit equation is and they ask you to find marginal profit, you just take the derivative of it. Okay. So that being said, let's try to get this last example finished up. We have a profit equation. They have already figured out the profit equation. Oh, I'm sorry, that's not the profit equation, that's the price equation. So the price of selling X units is 9 minus 0.03X. So the revenue we bring in is just how many did we sell times their price. So look at what they've set up here. The revenue is, I've sold 20 items, the price was $4, 20 times 4. So it's just the number I sell times the price per unit. So that's where they came up with that. Okay. It says use the marginal revenue function to estimate the revenue obtained from selling 101 barbecue. Okay. So we know this. Or it's negative, they put it in descending order. And they want us to estimate. So when they say the word estimate, that's the first formula we did today. Okay, so what is the derivative? Well, the derivative is just going to be negative 0.06x plus 9. So think about 101. They did that on purpose. Our A is 100. Our h is 1, so we need to estimate a plus h, or 101. Okay? So our approximate revenue at 101 is going to be our function at 100 plus 1 times our derivative at, sorry, I made it f again, our derivative at 100. So we just got to plug in. So if we plug 100 into that, 100 into our function is 600. And then 1 times anything, you don't really need anymore. Our derivative at 100 is, let's see, our derivative at 100 is 3, isn't that? Because that would be 100 times, that would be 6. Yeah, that's 3. So the revenue at 101 is approximately 6. And there's a little piece I think I need to add, but let me, I don't do the business applications as often as I do the physics ones, so we might revisit this problem a little bit at the beginning of class tomorrow. Okay, so this is your assignment. We're going to work on it in class tomorrow. That's the main thing on the agenda for tomorrow, okay? There you go.